The production cycle begins at the source, where dairy cows graze across open green pastures under natural sunlight, converting raw agricultural input into the foundation of the entire process. Robotic milking clusters attach through infrared guidance, maximizing yield while maintaining strict physiological safety standards. Centrifugal pumps drive liquid through transparent conduits, monitoring flow velocity to prevent early protein shear. Pneumatic manifolds engage with arriving vessels, establishing a closed-loop system for high-volume raw product reception. Hydraulic coupling secures the transfer interface, eliminating atmospheric exposure before the milk enters primary filtration. Digital flow meters record volumetric data instantly, anchoring the traceability chain for the entire production batch. Multi-stage stainless filters intercept coarse particles, refining the liquid texture prior to bulk silo storage. Insulated silos maintain a constant 4-degree environment, preserving molecular integrity before the standardization phase begins. Automated valves navigate the flow path, directing raw product into high-speed centrifugal separation modules. Mechanical drives accelerate the separator bowl, utilizing G-force to isolate fat globules from the skin. Sample probes extract micro volumes under vacuum, delivering representative data for real-time fat content adjustment. Rotary separation achieves precise lipid balance, defining the final nutritional profile for global market requirements. Stabilized drive shafts eliminate vibration harmonics, ensuring mechanical longevity during continuous 24-hour operation. Dual streams emerge through pressure-regulated valves, separating cream and skim for specialized recipe blending. Plate exchangers initiate thermal treatment, utilizing counter-current flow to maximize heat transfer efficiency. Pressurized steam conduits elevate temperatures rapidly, neutralizing microbial activity without degrading essential milk proteins. Thermal holding tubes verify the pasteurization peak, securing biological safety before the liquid reaches evaporation. Regenerative cooling cycles recapture thermal energy, stabilizing the product for long-term concentrate storage. Buffer tanks regulate the downstream pressure, providing a steady feed for the high-capacity evaporation system. Piston pumps generate intense forward force, pushing standardized milk into the primary falling film towers. Vertical evaporator tubes facilitate moisture removal, utilizing low-temperature boiling points under a controlled vacuum. Gravity-fed cascades create a thin film, accelerating water evaporation while protecting heat-sensitive dairy nutrients. Vapor separators extract steam from the concentrate, concentrating the solids into a dense liquid state. Negative pressure sensors modulate the vacuum intensity, preventing thermal stress during the final thickening process. High-viscosity pipes transfer the concentrate between stages, increasing total solids concentration with every pass. Sight glasses reveal the changing density, providing visual confirmation of the product's evolving physical state. Homogenizers shear fat particles at 200 bar, ensuring a uniform emulsion for the upcoming drying stage. Density meters validate the specific gravity, confirming the concentrate is ready for high-pressure atomization. Intermediate holding vessels stabilize the concentrate, maintaining optimal flow rates for the spray dryer feed. High-pressure pumps deliver the final concentrate, generating the kinetic energy required for microscopic nozzle dispersion. The drying tower dominates the facility core, engineered to transform liquid into solid instantaneously. Intake air filters remove submicron contaminants, ensuring only sterile air enters the thermal heaters. Gas burners ignite within the air handling unit, generating the massive thermal energy needed for dehydration. Thermal thermocouples track the rising heat, stabilizing the intake air at 180 degrees Celsius. Insulated ducts channel the hot air stream, focusing energy into the top of the drying chamber. The atomizer assembly sits at the tower peak, prepared to disperse concentrate into the heat. Rotary wheels accelerate to 30,000 RPM, utilizing centrifugal shearing to create a uniform particle mist. Nozzle arrays inject the pressurized concentrate, increasing surface area for rapid moisture extraction in milliseconds. Vortex air patterns swirl the droplets, suspending them in a hot air environment for maximum evaporation. Moisture evaporates upon contact, leaving behind solid milk particles that descend through the drying zone. Dried powder cascades into the conical base, separating from the airstream for primary collection. Pneumatic hammers strike the external shell, utilizing vibration to prevent powder adhesion on internal walls. Rotary airlocks discharge the fresh powder, maintaining the internal pressure balance of the drying chamber. Cyclones utilize centrifugal force to recover fine particles, maximizing yield from the exhausted airstream. High-velocity air spirals within the cyclone, forcing powder downward, while air exits through the top. Collection hoppers gather the cyclone fines, reintroducing them into the main product flow for consistency. Exhaust filtration systems scrub the air, ensuring zero product loss and meeting environmental emission standards. Pneumatic transport pipes vibrate with product flow, moving warm powder towards the fluidized cooling bed. The fluidized bed receives the raw powder, initiating the final stage of moisture and temperature stabilization. Perforated decks vibrate at high frequencies, allowing conditioned air to pass through the powder layer. Particles jump in a fluid state, achieving total thermal equilibrium through constant air-to-solid contact. Hygrometers measure the residual moisture, validating a final dry state of exactly 3%. Centrifugal blowers deliver chilled, filtered air, reducing the powder temperature to prevent fat oxidation. Sifting units engage ultra-fine screens, eliminating any oversized aggregates to ensure a perfect powder texture. Vibratory sieves process the final output, maintaining a uniform particle size for optimal rehydration properties. Rare earth magnets monitor the flow path, providing a final physical safeguard against microscopic metal contaminants. Clean-in-place reservoirs stand by, prepared to sanitize the entire system with automated chemical cycles. Rotating spray balls deploy high-pressure jets, ensuring every internal surface meets pharmaceutical hygiene levels. HMI panels track every process variable, providing a digital twin of the entire drying operation. Storage silos buffer the finished powder, protecting the product integrity before it reaches the canning line. Magnetic conveyors accelerate empty cans, positioning them for high-speed integration into the filling circuit. Automated inverters flip the vessels, utilizing ionized air bursts to neutralize and extract microscopic dust. The sterilization tunnel activates high-intensity UVC lamps, eradicating surface bacteria through DNA-disrupting light. Violet light arrays saturate the internal surfaces, ensuring a sterile vessel for the dairy product. Dosage sensors verify UV intensity, logging safety data for every container passing through the zone. Robotic dispensers drop plastic scoops, utilizing high-speed synchronization to match the conveyor velocity. Visual sensors confirm scoop placement, ensuring each can contains the required measuring tool before filling. Rotary filling carousels engage the cans, dispensing milk powder with precise volumetric mechanical control. Telescopic heads lower into the tins, minimizing dust generation during the high-speed powder deposit. Integrated vibration plates settle the powder, optimizing the headspace for the final nitrogen injection. Dynamic check weighers verify the mass, instantly rejecting any unit falling outside the strict weight tolerance. Edge cleaning vacuums sweep the rim, removing residual powder to ensure a perfect metal-to-metal seal. Cans enter the vacuum sealing module, where atmospheric air is extracted to prevent future oxidation. Lid chutes dispense aluminum seals, aligning them perfectly with the top of the pressurized cans. Nitrogen nozzles purge the headspace, replacing oxygen with inert gas to preserve product freshness. Pressure sensors monitor the vacuum drop, confirming the removal of air before the final seal. Stainless manifolds supply high-purity nitrogen, maintaining the inert environment across the entire packaging line. The rotary seamer clamps the assembly, initiating the double-seam mechanical fold in a gas-rich environment. Mechanical chucks lock the lid, preparing the metal edges for high-pressure orbital deformation. Seaming rollers execute the five-fold seam, creating a hermetic barrier against the external environment. The seaming head rotates at 1200 RPM, ensuring mechanical consistency across millions of units. Sealed cans exit the chamber, transitioning to the final stage of surface decontamination and coating. High-pressure water jets sanitize the exterior, removing trace elements before the product enters logistics. Air knives strip moisture from the cans, preparing the metal surface for laser batch identification. Capping modules snap plastic over lids into place, providing secondary protection for the internal seal. Application rollers verify the cap tension, ensuring the product is secure for long-distance transport. Laser coaters etch the batch data, creating a permanent, unalterable record on the can's base. Ultraviolet pulses vaporize the metal surface, forming precise alphanumeric characters for global traceability. Vision systems inspect the etching, utilizing AI to verify the accuracy of the production timestamp. The finished stream moves towards final inspection, marking the transition from production to quality validation. X-ray inspection tunnels scan every unit, utilizing high-frequency waves to detect internal physical contaminants. Imaging software analyzes density variations, flagging any foreign objects with sub-millimeter precision. Pneumatic ejectors remove flagged units, maintaining a zero-defect flow for the final packaging stage. Diverter gates extract random samples, sending them to the laboratory for final microbiological clearance. Microbiology labs operate under laminar flow, ensuring a sterile environment for rigorous pathogen testing. Precision pipettes prepare agar cultures, testing for the presence of aerobic and anaerobic bacteria. Incubators accelerate microbial growth, allowing technicians to verify total sterility over a 48-hour window. Visual inspection confirms zero colony growth, providing the final biological green light for product release. Chromatography units measure vitamin levels, validating the nutritional claims against the laboratory standard. Spectral data confirms chemical purity, ensuring no contaminants have entered the production stream. Mechanical collators group the cans, preparing them for high-speed insertion into shipping containers. Case erectors utilize vacuum pads to form boxes, establishing the primary structure for logistics. Plungers slide the cans into the cardboard, utilizing fluid motion to prevent surface scratches. Automated tapers seal the flaps, applying pressure-sensitive adhesive for a secure shipping bond. Inkjet printers apply shipping codes, linking each case to the master production database. Articulated robots initiate the palletizing phase, moving with high-torque precision to stack the cases. Interlocking patterns maximize pallet stability, ensuring the load remains secure during ocean transit. Pallet wrappers rotate the load, applying stretch film to create a unified logistics unit. High-tension film locks the boxes, protecting the product from moisture during global distribution. Autonomous vehicles navigate the warehouse, transporting finished pallets to the automated storage racks. High bay systems organize the inventory, utilizing digital slotting to optimize the shipping schedule. The production cycle concludes as validated dairy products ship, reaching global markets with total integrity.